Right, here we're going to differentiate functions of the form e to the x, and our most basic function f of x equals e to the x. The derived function is actually e to the x, so it's a special function that has itself as its derivative. Obviously, just differentiating e to the x is not going to be very exciting, so generally speaking these functions are composites with other functions. So in general your exponential functions would be of the form e to some other function f of x, and so this is a composition. So g dash of x is the derivative of f dash x multiplied by e to the f of x. So that's what we're going to be using in these examples. The first example, just a very straightforward one. F of x equals e to the 5x. So f dash of x, the derivative of e to the 5x is simply e to the 5x, and then you've got to multiply by the derivative of the 5x, which is 5, and so this would be written as 5e to the 5x. You may have to use a bit of manipulation and changing these things around before you are able to differentiate them. So for example, this one, 6 over e to the 2x. We can't differentiate it as it stands there. We need to move that e to the 2x up to the top line, and it's the same as moving any other power up to the top line. The power changes from positive to negative, so this is 6e to the negative 2x. So now we can differentiate this. The 6 can just be left alone. The e to the negative 2x differentiates and stays e to the negative 2x, and then we need to multiply by the derivative of negative 2x, which is negative 2, and then simplifying that, negative 12 e to the negative 2x. So all of these exponential functions that you're differentiating are composite functions. So you've got this general form here where you've got e to the f of x, so you've got the derivative as being f dash of x, e to the f of x, and then these two examples.